So, today we are going to answer one question, that is, what makes an optimization problem difficult? So, the point that we need to address here is when we are talking about difficulty, what is this difficulty? So, let us be precise. In optimization, we are always trying to find the values of some variables. We call them as the decision variables that maximizes or minimizes some objective function. So these decision variables either they maximize or minimize some objective function. And this objective function, it is also subject to certain constraints. So if I talk about it formally, suppose you have to minimize fx, where x is a vector of decision variables. Possibly subject to certain constraint like gx less than equal to 0 and hx is equal to 0. So now the difficulty is not just the problem size. A problem can be small in terms of number of variables, but it still can be very hard to solve. And a problem can have millions of variables, but it may be easy because of its mathematical structure. So difficulty comes from four scopes. Difficulty, it primarily comes from four sources: shape of the problem landscape, nature of the constraints, conflict between multiple objectives, presence of noise or deception. We will go through each one of these points. So think of it this way. Imagine you are blindfolded on a terrain and your job is to find the lowest valley. So if the terrain is a single smooth bowl, one valley, smooth slopes everywhere. It is very easy. You start from here, you come here, you get there. But what if the terrain is a jagged mountain range with thousands of valleys, some deeper than the others, separated by ridges you can't even see? So now walking downhill leads you to a local trap, a valley that looks like the answer, but it isn't. So that's the essence of what makes an optimization problem hard. The concept of a fitness landscape. Fitness functions you will hear from time to time. So the concept of a fitness landscape is the one of the most important mental models in all the types of optimization. So let me walk you through it properly. The fitness landscape is a mapping from the search space where all possible solutions exist, all possible solution exist to the objective value. How good each solution is. So this is the mapping. So if you had two decision variables, you could imagine this as a 3D surface. X, Y are your variables, and the height of each point is the objective value. So imagine it in a 3D surface. So I will give more examples which will clear you. And the real problems that we see around us, they have hundreds or thousands of variables. So the landscape, the landscape, it is very high dimensional. So this topic, high dimensional space. So the landscape is high dimensional that you can't even visualize. So that is, but the metaphor still holds. So you are having those same things, the variables, the constraints, all those things. However, the dimension is very high. So we can define it as, when it comes to dimension, unimodal, multimodal, deceptive. Three scenarios when it comes to the dimension. So in case of unimodal, it will have only one global optimum. Here, the gradient descent type algorithms they work. So every algorithm they find it very quickly. So solutions are found very quickly. Like we saw in the case of the bowl, something like that. Multimodal means there are many local optima, easy to get trapped. So here we require exploration. So once we get certain solution, it should not be like we have finalized. We should look for certain more options. Then there is the deceptive. Here the local signals actively mislead. Suppose gradient point away from the global optima. So this is confusing. So this is more serious case. So this is the modality. So when we are talking about the dimension space, we will talk when we talk about modality, we have these three modal scenarios. If we talk about specifically modality, so you can see there are three different scenarios. Second, in the dimension, we have the scenario of ruggedness. It is about how rapidly does the landscape change as you move through the search space. A smooth landscape, like how does landscape change if you move? A smooth landscape changes gradually. So nearby solutions have similar quality. A rugged landscape changes wildly. So your neighbors can be dramatically better or worse than you. So this ruggedness, this breaks the it breaks the gradient based methods. So we saw that these kind of methods they give solutions in certain cases, but if the scenario, okay, if you are talking about the dimension, if you talk about the ruggedness of the search space, if itself it is very highly rugged, then it breaks these kind of algorithms. So you cannot expect much better solution if the terrain is rugged. Third, epistasis. So this is a genetic term that we have borrowed. It means the variables in your problem interact. So there's an interaction among the variables. So this again leads to more complex scenarios. So the effect of changing one variable depends on the value of the other. So if I try to change x, it is again depending on y. So when the epistasis is high, you can't optimize each variable independently. So suppose I want to improve x, but then this is also tied. I need to look into this. There might be more. Again, this will get impacted. So this is known as epistasis. So this leads to problem. So everything is coupled, and this is what also causes the ruggedness. So let me give one example of real life. Suppose you are configuring a network. You have two variables, bandwidth allocation and queue size. If the epistasis is low, increasing the bandwidth allocation always helps, regardless of the queue size. This doesn't matter. However, if the epistasis is high, means these are coupled very tightly. So if I increase the bandwidth allocation, it only helps when the queue size is above certain threshold. Below that threshold, this is a problem. So you cannot optimize them independently. So certain problems that we deal with in our day-to-day life, here the epistasis is often very high. So if I want to improve, this doesn't mean that we'll not try to improve, but the thing is that we need to tune them jointly in certain way that the overall scenario improves without getting lots of compromises. Another landscape property that we can look into is neutrality. This is when a large portion of the landscape have some or very similar fitness values, like a flat plateau. So navigation here is tricky because there is no gradient signal at all. So you're wandering without any feedback, and you might stop somewhere and you are like clueless. So are you getting? So this is another scenario. Now let us talk about the constraints. This is the second major source of difficulty. So we saw the landscape difficulties, the landscape problems. Now we have the issues of constraint. So constraints also come with their own set of difficulty. Suppose a problem is purely unconstrained. So at any point in the search space, there is a valid solution. So you can explore very freely. constraints, they shrink the valid region. So they define certain feasible space. So they will define certain feasible space inside the whole search space, and solution outside this search space is illegal. So the constraints, these are also like when we have the constraint, like if the problem is not unconstrained, in this case also the constraints, they are also of certain types. Suppose we have the inequality constraints and the equality constraints. Inequality constraints are like, for example, you are given a constraint gx is less than equal to 0. So the solution must be below some limit. For example, the total power consumption shall not exceed 100 watt. And in equality constraint, it is like hx is equal to 0. Say a solution must satisfy this exact solution or exact condition. For example, the sum of all the assigned workloads must be equal to 100. In both the cases, this is certain kind of constraint. So a key difficulty is that the global optimum of the unconstrained problem is often outside the feasible region. So you are not just finding the best point on the landscape, you are just finding the best point on the restricted slice of it. And that slice may be irregular, disconnected, very thin, and so many problems. Okay, so suppose the actual solution lies somewhere here, but we are unable to go here because of certain constraints and all. So this is also certain type of problem that we need to look into. So what makes the constraint optimization hard isn't just that a feasible region is smaller, it's the shape and topology of that region. And another word that you will hear a lot, that is if the feasible region is convex or non-convex. So when it comes to convex, any line between two feasible points stays inside the region. So the constraint handling is manageable. Standard mathematical programming works well in convex problems. But in case of non-convex, it has holes, disconnected islands, narrow corridors, things get really ugly and out of hand. And an algorithm exploring from, suppose one island has no path to go to the other. It might not even know that this one exists. So the solution might be here, but it doesn't know, and it doesn't know how to go there. So this is the scenario of the constraint. Apart from that, the if you talk about the constraint types, these are also like soft constraint and hard. Here, the in case of soft constraint, the violations are penalized but allowed. So adds a penalty term to the objective, but it is easier to handle but requires careful penalty tuning. So you are ready to take up certain penalty. However, it is manageable. But in case of hard constraint, violations make the solutions completely invalid. So we cannot, like it is strictly enforced and it significantly shrinks the reachable search space. So this, if you are dealing with a hard constraint problem, it again increases the difficulty. So this is another combination that we can get to see. So how you are handling like any algorithm that you are proposing. So how it is handling the constraints, it either makes or breaks the algorithm. And if we talk about our proposal of metaheuristics, it uses tricks like penalty function where penalizing infeasible solutions in the objective, or we might have repair operators that push the infeasible solutions back into the feasible region. Will cover these things. in the when we implement a specific algorithm. Third source of difficulty is multiple conflicting objectives. So this is the third one, multiple conflicting objectives. So the most real problems don't have a single objective. So if you look around us in the problems around us, like engineering problems, so these are mostly multi objective. So suppose you want to minimize cost. If you talk about a network, minimize cost, maximize performance, minimize energy consumption, minimize latency, all at once. These goals often conflict. So, doing better in one may bring down others. So, this isn't a technicality, it's a fundamental property of reality. Buying a faster car costs more money, it will take more petrol. So, in terms of network scenarios, having more servers, it reduces the latency. So you're happy, but it increases the energy. Now you're sad. So there is no free lunch. So not just in algorithm selection, but in optimization itself, there is a problem. So when you're trying to optimize, you're going to answer all these questions. In single objective optimization, the answer is a single point. The best solution, that is all. But in multi objective optimization, there is no single best answer. You will often see when you're experimenting, certain things you're able to improve, other things it becomes worse. This is an endless fight. Like it's very difficult to get all the things together. If you're doing the thing, implementing the algorithm very genuinely, you will see it is very difficult to get all the things together in one plate. So this is another concept. So um, we can take certain example. So if we ask one question to us, suppose that what does the multi-objective, why does the multi-objective nature that we're talking about, it makes the things harder. So multi-objective, why it makes the things harder? Because the search landscape isn't a scalar surface anymore. It's a vector valued landscape. So you can't just compare two solutions with a single number, like which solution is better. It has no clean answer. An algorithm that assume a single objective value like a basic gradient descent simply doesn't apply. We discussed this before also. Gradient descent, it simply doesn't apply. That is why multi-objective metaheuristics, like for example, NSGA, etc., or even multi-objective variations of veil optimization, metaheuristics, all this, they are specifically engineered to find and maintain a diverse set of Pareto optimal solutions simultaneously. Now let us come to the final one, the fourth difficulty, and it is this is often overlooked or not appreciated. That is the noise or deception. So suppose you are able to manage all the other difficulties, yet you are not getting the optimal solution. One reason could be the noise in the problem itself. So let us start with the noise. If we talk about it, like in many engineering systems, evaluating the objective function isn't clean. There's a randomness involved. So you simulate a network under load and measured latency, But when it comes to the real life, we see that certain problems like jitter and all these things also come, and they often impact. So our algorithm should be robust enough, first of all, this selection. And if you are applying certain modifications, in this case, it should be robust enough to handle noise and deception. If it is not, in that case also, you might not get proper solution. Or you might get a solution that is fine with certain specific number of nodes, or when you're not taking into consideration the challenges that can happen apart from the scenarios of this simulator. In that case also, if your algorithm is not flexible enough to adjust the noise or deception, then it is again going to fail. So these four difficulties that we talked today, I hope you are clear with these things. And if you have any query, you can put in the comment. Thanks.